So hi everyone, I'm Yicheng, a postdoc in UC-HiPACC. I'm working with David and Sandy. So the reason why I switched with Neil is that I would like to let all your series finish first, and then I can step forward to tell you what our observed says in the universe. So this work, in this work, I'm going to talk about Clumpy star-forming galaxies from redshift 3 to redshift 0.5, and this work is done together with many members in the CANDELS team. So as you know, clumps are important, and it's an important feature of high redshift galaxies, and people are interested in how these clumps are formed, and are they formed due to violent instability, minor merger, or major merger? And once they formed, how they evolved across the cosmic time? Are they going to form the progenitor of today's barge, or are they going to quickly disrupted by feedback? Do they have any connection with the AGN or supermassive black hole? So today I will talk three aspects of clumps that we observed through HST broadband image, and I'm trying to give you a big picture of what we know about the clumps across the cosmic time. So lots of observational work on clumps has been done with the AO-assisted IFU, for example, from Ganzo's group, or HST GRISMA, for example, from Stanwood's work. But still, I think the HST broadband image has its own advantage because it can allow you to investigate a broad, wide redshift range, and it will allow you to go to small fainter galaxies, and also it allows you to get a much larger sample. So the first aspect is the physical properties of clumps at redshift 2. It's from my paper 2012. And the second one is the clumpy fraction, how many star-forming galaxies are clumpy, and how this fraction change from redshift 3 to redshift 0.5. This is a paper we just submitted. And the last one is the kinematic connection between clumps and the kinematics of galaxies. This is a very preliminary result. So part 2, the physical properties of clumps. So here we have 10 galaxies selected from HUDF. They all have spectroscopic redshift from 1.5 to 2.5, stellar mass greater than 10 to 10, and they are star-forming. So for each galaxy, we identified the giant clump, from its UV, rest frame UV images, and we measured, because in HUDF we have 7 HST bands, then we can measure the specially resolved SCD for each clump, and we can get physical properties of stellar mass, star formation rate, age of each clump. So this is a result. This is star formation rate versus stellar mass for clumps, red, and for whole galaxies or for disks. Whole galaxies here are black and disks blue. So clumps are still blue, and they blue in rest frame UV and optical color, and they have higher specific star formation rate than disks, although the star formation is still dominated by disk. And also, if you look at the rest frame UV color of clumps as a function of their distance to the center of galaxies, you can find this trend, and the central clumps are redder and outskirts clumps are blue. Because we have run SD fitting on each clump, so we can convert this trend of rest frame color to the trend of the physical properties. Here is a specific star formation rate, age, and dust extinction, and stellar mass density. So looks like when clumps go into the center, they become redder, and they become denser, older, and the star formation rate decrease. So this result is kind of consistent with the scenario that once you form the clumps, due to whatever reason, the clumps tend to migrate into the galactic center to merge and form the barge of today's in today's disks. But as you may know, the results of part 1 is just based on 10 galaxies. We may want to increase the sample and to get a whole view of how this clump properties changes from high redshift to low redshift. But before that, we have to determine one thing, that is how to define a clump when you go from high redshift to low redshift, because your observational effect changes, your spatial resolution changes, and your sensitivity changes. So we need a physical definition of clumps across a cosmic time, but unfortunately, now we don't have such a definition in observation. So as a result, we don't know how many star-forming galaxies are clumpy, and we don't know how much clumps contribute to their galaxies. So the key point is here. This is M101, our backyard galaxy, and this is a guy at redshift 1. Do you think they are physically, intrinsically different, or this one is just a blurred version of M101 due to the low spatial resolution? So in our submitted paper, we proposed a roadmap to how to define clump in a more physical way. So we have a sample of galaxies, and we pick up some nearby galaxies, M101, M83, M33, and then we try to match all the observational effects of these nearby galaxies. We shrink the size to match the size of sample in our galaxies. We make them fainter to match the apparent magnitude of galaxies. And then we put all these real galaxies and redshifted galaxies into a blob finder. So here, blob means discrete star formation region. I'm not calling it clump because we haven't defined clump yet here. And then you got real blobs, fake blobs, and then you do a comparison. So that will allow you to pick up that the real unique blobs that you should call clumps, because they are not the anything that you can explain by nearby galaxies. So here's briefly our sample. Is from CANDELS, Good South, and UDS, and we pick up all galaxies from 0.5 to redshift 3, and they are star-forming, massive, and we also use like face-on-like galaxies because we want to avoid the dust extinction, and also we use large galaxies, bright galaxies. So this is our clump finder. So for each galaxy, we smooth its original UV rest frame UV images, get smooth image, and then we subtract the smooth image to get the contrast image. We only pick up the pixels with a high signal-to-noise ratio, and then we run extract on this filtered image. We got this, then we determined, say, 6 blobs in this image. That's how our blob finder works. And we did the same thing for the real galaxies and for fake M101 that we redshifted to the same redshift. So here is the plot shows the fractional luminosity function of clumps. Y-axis is the number of blobs per galaxy, and the x-axis is the rest frame UV luminosity of blobs as a function. UV luminosity of blobs rescaled by the total UV luminosity of a galaxy. So black histogram is the function of real blobs, and the red histogram is a function of the blobs in the redshifted nearby galaxies. So you can see in the faint end, the redshifted nearby galaxies did a quite good job to explain the shape of the fractional luminosity function. But only when you go to the very bright end, so the real galaxies has more this bright and large clumps that cannot be explained by the redshift nearby blobs. So that's the solid line here is our definition of clumps, that we define clumps as discrete star formation regions that contributes at least 8% of the total UV light of the galaxies. And we think this is a more physical definition of clumps than any other ways that, for example, you define clumps from visual inspection. So given this definition, we can do a statistic to say how many star-forming galaxies in our sample contain at least one offset UV bright clumps. So this is the result. The colors means different stellar mass spins, and at high redshift, all galaxies in all stellar mass spins, galaxies have like 60% of chance to be clumpy galaxies. But when you go to low redshift, the more massive clumpy fraction of massive galaxies drop fast. And when you go to 0.5, it's like 15% or 20%. But for intermediate galaxies, it drops slowly. For low mass galaxies, the fraction is almost always 60%. So here, black solid line shows the sigma over v, the velocity dispersion over the circular velocity from the model, VDI model of Casiato et al. 2012. So this line, we arbitrarily scaled this line to see whether the trend matches the trend of massive galaxies. So it does a very good job, but you should keep in mind this is arbitrarily scaled. And another thing is this line cannot explain the trend of intermediate mass and low mass galaxies. Part of the reason is we don't have a reliable VDI prediction for low mass galaxies. But if you look at the minor merger rate, minor merger fraction from Jennifer Loss's paper, and if you assume a reasonable visibility time scale, for example, 1.5 or 2 gig years for minor merger, and that the minor merger fraction is kind of consistent with the Clumpy fraction of intermediate mass or low mass galaxies. But for major merger, only if you assume the very long visibility time scale, for example, 3 gig year, it can match the fraction, Clumpy fraction of massive galaxies. But we all know that the visibility time scale for major merger is quite short, usually less than 1 gig year. So this is a kind of summary of my part 2. VDI seems a reasonable explanation for the Clumpy fraction for massive galaxies. Minor merger may be good for intermediate mass or low mass galaxies. Major merger we can rule out for all. So remember, this line I said is arbitrarily scaled. So do we have any way to constrain this this prediction of VDI better? So here in this side we have a Clumpy fraction. Actually, in this side we have this settled fraction from Susan Carlson et al. Using deep to data. So the settled fraction, so the settled galaxies means the galaxies with the circular velocity 3 times larger than the velocity dispersion. So that means a settled galaxies is a galaxies with a motion in order, and unsettled galaxies actually velocity dispersion dominated the galaxies and is in non-ordered motion. So how about if we compare the settled fraction with our Clumpy fraction? Do they match? If they match, they will tell us that most clumps are found in actually settled galaxies. So here is the result. I don't know if you can see the open symbols here. Those are the settled fraction from Susan's data, and you can see actually for massive galaxies, the match is quite good, and also for intermediate galaxies, it's still okay. But for low mass galaxies, the settled fraction is significantly below the Clumpy fraction. So now this is not arbitrary scaled relation at all. So this is this tells us for massive galaxies, you will be harder and harder to find the Clumpy galaxies because most of the disks at low redshift are actually settled. And another thing is you can compare the UV luminosity of clumps found in different galaxies. So this is again circular velocity over dispersion. This is the settling threshold. Galaxies in this part are settled. Galaxies in this part are not settled. They are velocity dispersion dominated. And this is kind of our clump definition. Every blobs above this line, we call it clumps. Below, it's just ordinary nearby counterpart of ordinary nearby H2 regions. So you can find that when you go from the unsettled, from settled galaxies to unsettled galaxies, the clumps with the blobs we find is have more and more chance to be called clumps. That's what the red squares tell you. For settled galaxies, almost the blob, the discrete star forming region are actually just normal nearby H2 regions. But when you go to these unsettled galaxies, the majority of blobs, discrete star-forming region, are called clumps. And also, if you just take into clumps above this clump threshold, the UV luminosity or fractional UV luminosity of clumps increase when you go from settled disks to unsettled disks. So that means, so again, this combined with the last slides that tell you you will have harder and harder time to find clumps in settled disks when you go to low redshift. And even you find some clumps, those clumps tend to be small clumps, small in terms of its UV luminosity. So again, this is still a very preliminary result. We are still trying to understand the physical mechanisms of this result. But here, this is my summary. We are tracing clumps from high redshift to low redshift. And we have studied the physical properties of clumps at ZF2. Clumps are blue with high specific star formation rate. And they are central clumps are redder, and outskirts clumps are blue. So it's kind of consistent with this inward migration scenario. Also, when you go from high redshift to low redshift, you need a physical definition of clumps. That's what we are still working on. And in our paper, we propose a definition based on the fractional UV luminosity of clumps. And we found 60% of star-forming galaxies at ZF3 are clumpy. And the evolution of clumpy fraction depends on the stellar mass of galaxies. The more massive the galaxies, the faster the clumpy fraction drop with the cosmic time. Also, we found some interesting connection between the clumps and the kinematics of the galaxies that you find the clumps at Z0.5. Thank you.
Time for a couple questions for Yicheng. Have you tried this procedure looking at the risk frame optical light? And you get a very different answer.
Yes. Clumps are not as prominent in the rest of frame optical as in rest of frame UV. So that's why we choose rest of frame UV to define clumps. And also, this is kind of consistent with the result that clumps have a high specific star formation rate because the stellar mass, let's assume that rest of frame optical is a better tracer of stellar mass. The stellar mass of clumps are quite small, but the star formation rate are relatively high. So
do you have a sense of, from your work or other people's work, some typical, like your threshold of 8% of the luminosity in this clump for you to call the clump? Do you have a sense of what stellar mass threshold that might correspond to for a typical clump color?
I would say 1 or 2%, something like that. Yeah, that's one thing we are going to measure. Use the whole candle sample. We are going to match the all the HS band images and try to get SCD for each clump, and we can determine the stellar mass. But 1 or 2% is just my guess based on my experience. No, we only include the off-center clumps.
Okay, well, we have coffee waiting for us, so I'm sure you guys have more questions for Yicheng, but you